Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to discuss the Markov property. As you can tell from the name, the Markov property is a central component of the Markov decision process. The reason we're devoting an entire lecture to the Markov property is because in the context of reinforcement learning, the Markov property looks a little different than what we've seen in the past. Let's review the Markov property in the strict mathematical sense. Suppose we have a sequence of x1 up to xt. We can define a conditional probability on xt given all the previous x's. Generally speaking, this can't be simplified. But if we assume that the Markov property is true, then it can. The Markov property specifies how many previous x's the current x depends on. So first order Markov means x of t depends only on x of t minus 1. Second order Markov means that x of t depends only on x of t minus 1 and x of t minus 2. In this course, we will be working with first order Markov only, and we typically just refer to this as the Markov property. Let's do a simple example of the Markov property. Let's consider the sentence, "Let's do a simple example." If I were to tell you, here are the previous words in my sentence, now predict the next word. The previous words are "let's do a simple," you can probably guess that the next word is example. Now I say the previous word is just simple. Can you predict the next word? Probably, but it's harder. What if the previous word is just Can you predict the next word? Probably not. But that's what the Markov assumption is. So you see that the Markov assumption can be quite limiting, but you can also define your problem such that it's not. So what does the Markov property look like in reinforcement learning? Recall that doing an action A of t, while in state S of t, produces two things. It produces the next state, S of t plus 1, and a reward, R of t plus 1. What the Markov property in this case says is that S of t plus 1 and R of t plus 1 depend only on A of t and S of t, but not any A or S before that. For convenience, we can also use our shorthand symbols, S, A, R, and S prime. So how is this different from the usual way we write the Markov property? Well, notice how this is a joint distribution on S prime and R. So it's telling us the joint distribution of two variables conditioned on two other variables. This is different from the usual Markov form, where we have only one variable on the left and one variable on the right. Given this joint conditional distribution, it is of course just a matter of using the rules of probability to find the marginal conditional distributions. For example, if we just want to know S prime given S and A, or we just want to know R, we can use these equations. Also note that for pretty much all cases we'll consider, these probabilities will be deterministic. That means the reward you get for going to the state will always be the same reward, and doing an action in a state will always bring you to the same next state. But it's good to know that these probabilities are defined if you need them, and they are also part of the core theory. As an example of how the Markov assumption is not necessarily limiting, we can look at a recent application of reinforcement learning. DeepMind used the concatenation of the four most recent frames in order to represent the current state. Strictly speaking, the state can be made up of anything from any time from past to current. We just typically think of the state right now to be something we are measuring right now, but that need not be the case. Note that we also need not use raw data to represent the state. The state can be made up of any data derived from the raw data. You might think of that as a feature transformation on the raw data. Essentially, any input from the agent sensors can be used to form the state.